me, but this is an important question. Is math a little bit easier to engage with and more interesting when we think of it as patterns instead of just rules?
Yes, sir.
Although I'm about to establish a rule that we don't throw our rulers around. Is it a little bit easier to kind of investigate and explore? Yeah. I'm glad someone at least feels that way. The rest of y'all, it makes me a little sad, but you know, I'll get over it. I think that math is beautiful when we start looking at it as patterns and relationships. So here's the thing. I know that a lot of us already have a lot of ideas down for number 5, right?
Right.
But even yesterday when we did numbers 1 through 4, did we learn new things beyond what we had already written down?
Yes.
Yes. So I need y'all engaged and paying attention. I need you sharing ideas, but I'm going to put more in there than you might necessarily already have, and you should have room to write some things down. So I need you to pause on what you're working on so we can focus on this together as a class. So, consider the data table given below. Create a real-world verbal description. So first things first, I want to hear some of those verbal descriptions because, again, this is where math becomes beautiful, that we find relationships. So, somebody, what's a story we came up with? Yes, ma'am.
There are 5 people went inside the store. Every hour, 3 more came in.
All right, so there's 5 people inside of the store, and every hour, 3 more people are coming in. Now, we're also assuming that no one left. Is that fair? It's wild. Man, I could not imagine being inside of a store for, I don't know, 3 hours. But I love the context. It establishes the ideas that at the beginning, not at hour 1, at hour 0, when everything started, there were 5 people and we're repeatedly adding how many? 3, right? Who else had their hands up for, what's up?
At work, my boss gave us 5 donuts each day. Oh, no, on Monday he gave us 5 donuts, and each day he gave us 3 more.
Okay, so you're counting Monday as day 0.
Yeah.
And then you're getting 3 more donuts every day. I hope you don't let them sit there forever, but I do like it, right? Starting at 5, and then getting 3 more every day. What else?
Avery earns 5 points for good behavior every day for 5 days. She earns 3 more points for the week.
Okay, so she earns 5 points every day for 5 days, and then 3 more points
Oh, okay.
at the end of the week?
So like the first day she earned 5 points.
Uh-huh. Second day she earns?
3 more points.
Oh, so she's earning 3 more points every day.
Yeah.
Gotcha. So you were saying, what you meant to say, and I think you probably had this written down, is that she already had 5 points. And I will say, her day on Monday, we'd have to count that as day 0. She has 5 points, and then every day after that, she's adding 3 more. Because remember, what makes a linear function linear?
Addition.
Not just addition.
Repeated addition.
Repeated addition. What are we repeatedly adding in this table?
3 plus 3.
Plus 3. Okay. You want to share one as well?
Yeah. Carrie is working on bodybuilding. She can already hold a 5-minute plank. Every week she adds like
I could not imagine doing a 5-minute plank. No way, no how. I'm impressed. All right. I got to get group 8. Y'all had a really fun one. What'd y'all come up with, story-wise?
Y'all get took over 5 people. Every minute he took 3 more. How many people did he take at 6 minutes?
All right, so Yogurt took over 5 people, and then every minute took over 3 more people. All right, and you added extra detail of how many people did Yogurt take over by 6 minutes. But remember, the function that we're looking at, do we want it to stop somewhere?
No, you want it
He wanted to keep going.
And it's not necessarily that we want to keep going, and yeah, I guess we do want to keep going, but it's more that we just want it to be able to represent any situation, any number of minutes. So you can say at 6 minutes, but we're not looking for that right now. Does that make sense? That's a good representation. Okay, so a couple of quick things. We got verbal descriptions. The idea of starting at 5 and repeatedly adding 3 every single time was really important there. Now, it says create a graph. How many of you actually created the graph before you tried to make the equation? Y'all did? Okay. If you're trying to write the equation, I need you to hear me very clearly on this. It is possible when you get more skill with it. But the equation is the hardest part of the math.
No, I just told to come.
I would have done a table, I would have done a graph, I would have done something else before I made the equation. Because here's the thing. A lot of y'all really did recognize we're repeatedly adding, so what type of function is this?
Linear function.
Alright, so we got a linear function here. And so, yes, we already know that the equation in general needs to be what?
F of x.
Okay, well, function notation, so f of x or y, but in general, what's the equation?
Y plus B.
Y equals mx plus b, or f of x equals mx plus b? And what I heard a lot of students say was m is
3.
slope, which is 3, right? But from what I heard,
So you add 3 every time.
because we're repeatedly adding 3, and we come back to that in a second. And I will remind you, 3 is being multiplied by x, because multiplication is repeated addition. Thank you. Okay, so yes, we are repeatedly adding 3 every time, but some groups were struggling with what b was. Some of us, and I think Mitra, you fell in this category, you said, I assume it has to be 5, but you weren't really sure why it was 5. Is that fair?
Mm-hmm.
Yeah? Okay? And that's okay, but I need you to hear me on this. Y'all are forgetting, first off, the name of this equation. Mathematicians are not original, they name it what it is. What is the name of this equation? It's a linear function, but this equation is slope intercept. If this m is my slope, the b is my intercept. Specifically, which intercept?
5.
The y-intercept. The y-intercept, right? So again, y'all, I need y'all paying attention. I need y'all engaging in this whole class conversation. You'll have more time to work in your groups. I need you paying attention up here. Right, we got a slope and we got a y-intercept, so 3 times x. Where can you most easily see a y-intercept? On a graph. Well, just on a graph, right? The y-intercept is easy to see on the graph. So if you weren't sure what the y-intercept was, go to a graph. Thank you. All right. I got one student in there. So now I will remind you, I didn't push this on any groups, but remember this graph has meaning. You all created different representation or different context, but your x-axis means something. A lot of us, the x-axis, the independent variable, was the hours or the minutes that have gone by or the days that have gone by, right? And so nope, that's meant 1 or 2, 3, 4. Make sure you include your context in here. And I'm actually going to go by 2s because I ran out of space. 4, 6, 8. By the way, do you have to go by 1s?
No.
No, you can go by whatever you need to. But remember, these are points. 0, 5. So my x value is? 0. My y value is?
5.
5. So 2, 4, 5 has got to be here. Then it's got to be
1.
1.
Go over 1, go up 8.
Okay, so 1, 8.
Go over 2, go up 11. Go over 3, go to 14.
Okay. Do I have a line there?
You do.
It's a little off because I don't have graph paper. Remember, graph paper is going to make our lives easier. But I want to emphasize a couple of details here. When I graph this, what is my y-intercept very clearly?
Up 3, up, wait.
My y-intercept.
5.
I'm intersecting here at 5. So plus what?
5.
5. So I would make a note if I were you. The y-intercept is easy to see on the graph. On this problem, so that you have this information in the future. Remember, I'm not just going over this for my sake. I already know this. If I'm going over it, this is going to help you. I would make notes on your work. The y-intercept is easier to see on the graph. The y-intercept is easier to see on the graph. But also, I need you to recognize the y-intercept is a point. It's a point on the y-axis, right? If you look on the y-axis, what does every point on the y-axis have in common?
Going up 3.
No, on the y-axis. I'm talking not on this function, just on the y-axis. If you pick out any point on the y-axis, what do they all have in common?
It's 0. Right?
What is 0?
The X.
The x. So you need to make a note to yourself here. The y-intercept always has an x value of 0.
You said always what?
What do you think? Always what?
Zero.
0. Remember, it's on the y-axis. Because here's the thing, I need you to hear me very clearly on this. When I first learned about x-intercepts and y-intercepts, and all the way through high school, I struggled to remember which one had 0 where. I struggled to remember that the y-intercept, the x value was 0. You know what helped me realize, and I've never forgotten it since? A graph. You can memorize all the rules in the world, or you can use your representations to help you. I start to picture in my mind a graph, and I say, if it's on the y-axis, I know that the y-axis is in between -1 and 1, and what's the only number directly in between -1 and 1? 0. The y-intercept is always going to have an x value of 0. Which means that the x-intercept is always going to have a y value of
0.
0.
Oh.
Right? That's how we remember it, is we look at the graph, we use our other representations to help make sense out of it. But it's important to notice that the y-intercept is a point and the x value is always 0. So really the way that we would write the y-intercept is 0, comma b. Whatever, where b is the y value of the y-intercept. Last couple of quick details here. First off, quick show of hands, does anyone have a question about that idea with the y-intercept and how to identify it more easily? Are we more comfortable with it now? Okay. One detail I want to point out is everyone I heard right now identified the fact that we are repeatedly adding 3, correct? Okay. And I saw a lot of people identify the fact here that we are adding 3. Do I need to pay attention to the independent variable at all? Trinity, why do you say yes?
Because sometimes it goes by different numbers, like odd numbers or even numbers.
Okay, sometimes it goes by odd numbers or even numbers, or maybe it goes by 3s or 1.5s. Because remember, the rate of change is called the what?
Slope.
The additive rate of change is called the slope, and how do we calculate slope?
Why equals everything.
Rise over run.
Remember,
Oh.
slope intercept form, but then it's rise divided by run, but it's also the change in y divided by the change in x. If you just look at this plus 3, do you have both the x and the y?
No.
No, that is only the change in y. Remember, our dependent variable is y. What is our change in x then? Plus 1. Is it always plus 1?
No.
So do you need to pay attention to the left-hand side of that table as well? Okay. So make sure, go back to the fundamentals. You can use any of those 3, but the 2 equations I recommend is, if it's a graph, I might think about rise divided by run. If it's anything else, I think of slope as change in y divided by change in x. If you want to do y2 minus y1 divided by x2 minus x1, go for it. But what I heard earlier is we don't remember that formula perfectly, so I might not do that one. Okay? Change in y divided by change in x is much easier to work with. The last, I'll wait a second. There's one more detail that I'm going to go over today, and this is where we'll end class. We'll pick up Tuesday, assuming that we're still open on Tuesday. I'm going to collect them in a second, but assuming that we're still open on Tuesday, I'm not saying that we are necessarily going to close, but there's just a lot of teachers out. I would not be surprised if they make a decision that we
Mr. Kenny, if we go online, you're gonna be sending all that work online.
I'll be putting stuff on Schoology, but it will not be the same amount of work. No.
Okay, I say.
Cause I can't learn online.
Yeah, I can't
Here's what,
online.
hey,
That's another
listen.
reason why I can't.
If I put anything online, what it'll be is it'll be practice, like solving equations, which we need more practice with anyways. Or creating equations. It will not be anything new, which I think is fair. Hold on.
Yeah.
Okay? Last detail I want to point out is we need to recognize that each of these representations, do they look different?
Yes,
But are they telling the same story?
yes.
Yes.
Equivalent.
They are equivalent, right? They look different, telling the same story, which is important because every point in this table and every point on this graph need to be the same, correct?
Correct.
Correct? Which also means that every point here and here should do what to this equation?
Make it the same.
Equivalent. Wait, what?
Those points should make this equation what?
True. Mathematically.
It was true. Yeah. I need you to hear me clearly on this because this is a detail a lot of students miss. The points on a graph and the points on the table matter because those are the points that are making this equation true. This equation gives us these points and you can check it, right? My output is 5. Is that equal to my input is 0? 3 times 0 plus 5. Is that a true statement? Yes. Check this point, 314. Is 14, the output, equal to 3 times my input is 3 plus 5?
Yeah.
Yes. The points on the graph and on the table matter for that equation. The points are what make that equation true. Now that's only some of the points. I need you to also notice this, even though it's not marked, that's a point as well, isn't it?
Yes, sir.
So that point, if I were to get it, should make that equation true. Okay? In fact, how many points are there actually? How many?
4.
There's one there, there's one here, one there, one there,
The whole
one here.
Yeah, the whole line.
What a line is, say it again.
Infinity.
Infinitely many. What a line actually is infinitely many points put right next to each other, but every single one of those points needs to make that equation true. The same thing is going to be true with the curves that we study later. These points matter. Okay? Notice a table can only show us some of the points. A graph is where we see all of them, or at least all within our view, but that equation is what's representing everything all at the same time. But I also don't want you to forget, tables, graphs, equations, we're going to use those heavily. But the point of all of these is to represent real-world things. Y'all created context, but some of us got to later problems and created context as well. All right? Now, I'm going to check this on Tuesday when we come back. If you have not finished number 6, I need you to finish number 6, because some of us are already on number 8, right? So, please make a note to yourself, if you have not finished number 6, I need you to finish number 6. Okay? Here is the actual homework. I think I did homework on here. Alright. So, did everyone get a new copy of this?
Yeah.
Nope.
Yes?
He did.
You did not?
Nope.
Anybody else need a copy? Because we're resubmitting. I don't know if you ever submitted that originally, but we're resubmitting that. Watch the videos, we went over stuff. So, if you don't, I need you to get out your graphic organizers, leave them on the desk, and I will collect them. I also need you to see this. Miss Courtney, who is our intern, she has to do videoing for her certification. So she needs these permission slips signed, and I will send out an email to parents about it as well. You don't have to approve, but please do because it will help her out a lot. But as long as you get it submitted, it will be a 10-point homework grade. So let's get those signed and returned, please. I will collect the homework in just a second, leave them on the desk. So don't forget the syllabus slip. There you go. All right. If you are turning in your graphic organizer later, it's only 10% off every day it's late. Or if you turn in after enrichment, it'll still be on time. I might do some work on that during enrichment. Please put up the rulers. You just